hi guys, my name is Nachiketa and welcome to my channel. In this video, we're going to cover activation functions and make sure that you watch my previous videos on machine learning and deep learning so that you completely understand this. But before talking about activation functions and different types that there are, let's start by understanding why we actually need activation functions, right? So this is how a typical neural network looks like, right? So for now, let's say that there's no concept of activation functions, right? And say you and me are neural network programmers or scientists who are programming the first neural network, right? So you have an input layer, a hidden layer, and an output layer, right? So what is the job of a neural network? You have inputs that come into the neural network, and the neural network has to assign certain weights to each input, which tells the neural network what is the importance of each input, right? For example, if you want to make a model that is predicting the price of a house based on certain factors like the size of the house, the number of rooms in the house, so these are certain inputs, right? So the neural network has to decide which input is more important and which input is less important. This importance is nothing but weights, right? So how do you get the output from the input, right? So let's represent the input as x1, x2 and x3. So your output y is nothing but w1 into x1 plus w2 into x2 plus w3 into x3 plus a constant term which we call bias. So w1, w2, w3 are weights which tell the neural network how important is x1, x2 and x3 for the particular output. You can see that the equation of y is nothing but that of a straight line. So basically you're finding a line that best fits a certain data, a certain pattern, right? So the problem over here is the output will always be a straight line. So this will only be valid for data which can be fitted on a line, which is linear, you can see. So for data which is non-linear, which have very complex pattern like this, for example, you won't be able to get an output using this neural network, right? Because y is always a linear combination of x1 and x2. Hence, you will always get a straight line equation. So what we need is to introduce non-linearity into the neural network so that it can be valid for patterns, for problems which are non-linear in nature, right? When the y is not varying linearly, even then your neural network should be valid. So here is where the concept of activation function comes in. Activation function was introduced to bring in non-linearity into the neural network, right? So it is very clear that when you have your input, simply multiplying them with the weights is not sufficient. So activation functions are nothing but simple functions that transform the input into something else, a different output, and brings about non-linearity, right? So different kinds of activation functions will transform the input differently, will convert the input into something else. Based on how they're transforming the input, you get different levels of accuracy. So we'll look at each activation functions one by one. So I'm going to start with the two most basic activation functions that there are, which is your sigmoid function and your Tanh function. So let's start with sigmoid first. I'm sorry for the poorly drawn graphs because this is the first time I'm using paint after a long time. I think it's pretty clear from the graph what this sigmoid function does. This is the equation for the sigmoid function. So it basically takes the input value, which is the x, right? So what this does, 1 upon, so it takes the x value and substitutes that in the equation, 1 upon 1 plus e raised to the power minus x. So you have input in the first layer. These inputs will be assigned certain weights to get the value of y. Now this value of y will be passed to the activation function. This is sigma of x. So instead of x, you'll have y over here, right? And when you give the value of y to the activation function, it will map that between 0 to 1 and get some output. Now this output will be again passed to the next layer, which will again apply a sigmoid function, and this process goes on again and again. So the benefit is that neural network can now predict outputs for data which is non-linear as well. Earlier it was restricted to only linear data, right? So that was for the sigmoid function, right? Now the next function that we use is Tanh. Why do we use a different function? Is because in neural networks it is convention, or it is normally preferred to get all your inputs standardized. What I mean by that is you might have one input which is in the range of thousands and lakhs and crores, and you might have one input which is in the range of 0 to 10 or 1 to 100, right? So we don't want such a difference in the ranges, so we standardize them so that all inputs are centered around 0, right? They could be plus or minus 0, but it's preferred that all values are centered around 0. So you can see clearly that in sigmoid function, all values will be centered around 0.5, right? So you can never achieve that with a sigmoid function. That is why we move on to Tanh function, which is, as you can see from the graph, it's simply a scaled and shifted version of your sigmoid function, right? Your sigmoid function had a range of 0 to 1. So that range is changed to -1 to +1. And now values are centered around 0. You can see the equation of tanh over here, and it looks pretty similar with the sigmoid function, right? It's just shifted and scaled. Benefit is that now values are centered around 0. Now both of these activation functions have a very big flaw, which is called as vanishing gradients, right? This is the reason why we need to go to different activation functions. Let me explain what this is with a small example, because this concept is a little tough to understand, so I'm going to try my best. I just need you to pay a lot of attention over here. Neural networks essentially have to learn weights, right? How do they learn weights? I've talked about this in my previous video. So what neural networks exactly do is, right, you have certain input and now you want to decide how important is that input in getting the correct output. So what neural networks do, they assign a random weight and check what output you're getting. If the output you're getting is wrong, they will see how wrong they were by calculating something as a cost function, or basically the error. So by trying different weights, their neural network is basically checking how much error are you getting, and it will try different weights until it gets the minimum error possible, right? So I'll give you a simple analogy to understand this. Say for example, you are turning the knob of a fan and you want to set it to some desired speed. The problem is the knob of the fan is not labeled, so you don't know at which point with what speed does it have. So what do? You automatically twist and turn the knob until you feel the perfect air pressure, right? So you'll start at say some point and you'll turn the knob and you'll feel the air pressure. If it does not feel good or if it's too much, then you twist and turn until you get the perfect air pressure. Imagine this knob as turning and tuning the weights of your neural network. So imagine you start at a random weight and you're getting some output, right? And you're getting some error. So as you're turning the knob, you're changing the weight and you're feeling a difference in the error. You're seeing how error changes, right? And you turn this knob until you get the minimum error. For this method to work, what is important over here? As you're changing the weight, you should observe a change in the output, right? So problem in tanh and both sigmoid is that after a certain point, for example in tanh you can see, let's say after around this point, the values are almost constant, right? They're almost equal to 1. So as you proceed along the x-axis, right, the output is not changing at all. So if the output is not changing, you will basically not be able to train your model, because you won't be able to try different weights because everything is giving you the same output. The same problem exists in the sigmoid function as well, right? After a certain value, all the values are almost constant. All the output is almost constant. Your activation function should change with respect to the input, right? So the change is nothing but the gradient. The gradient for the sigmoid function is maximum at the center at around 0.5, right? Around this region. And the slope it has is 0.25. For tanh function, the slope is a little more than the sigmoid function. I think it's around 0.38 or 0.45, which is also not very good, right? So this gradient is very small. So as the output is being sent to further and further layers, this gradient gets smaller and smaller because it has a multiplying effect. So that is why we say that when we're using sigmoid function and tanh function, you have the vanishing gradient effect, because as the output is being passed to next layers, your gradient becomes almost 0. So you're not able to tune the weights because you're not observing a change in the output. So these two functions cannot be used in your hidden layers normally, right? So what do? That's why we came up with another activation function, which is one of the most used activation functions in the world, which is your Relu function. So to counter the problem of vanishing gradients, we use an activation function called Relu, which stands for rectified linear unit. Alright, it's pretty simple. You can see the function is simply max of 0, x. So if the value is greater than 0, it will remain as it is. Otherwise, it will be converted into 0. So all negative values are mapped to 0 and the other values remain as it is. So on first appearance, this may look like a linear function, but it is not. It's a non-linear function because it's bending at 0, right? And it cannot be defined using the equation of a straight line. So this is a non-linear function and it gives you one of the most highest accuracy when you try it experimentally, right? So this is the solution for sigmoid and tanh. And this activation function gives you one of the best accuracies when compared to other activation functions. However, there is one problem that all values less than 0 are mapped to 0, right? Are converted into 0. So there is the problem of vanishing gradient for negative values. right? So either you convert all values into positive whenever you're processing in the neural network. So to counter the problem that we face in Relu, we come up with the activation function called Leaky Relu, which is just a slight modification. So if the value is greater than 0, it's same as x, just as in the Relu function. But if it's less than 0, we create an equation of a new straight line, which is a into x, where a is the slope of the line. So a is conventionally taken as 0.01, but you can take it any value. The point is that the function should be non-linear, and for negative value of x, it's not being mapped to 0. And these two functions have one of the highest accuracies. So the last activation function is your SoftMax function, which is the same as Sigmoid function, but Sigmoid function is used for binary classification. It gives you an output between 0 and 1, right? So 0 means it belongs to one class. When the output is 1, it means it belongs to a different class. So when you have multiple classes, right, say you have an image and you want to predict if it's a table, chair, fan, car, AC, you have multiple classes of outputs. What you do is you use the softmax function. So when you're using softmax, so say you have 10 classes to predict and you're using 10 neurons in the output. So each neuron will now output a value between 0 and 1, same as in Sigmoid, but the sum of the output of all the neurons will be 1. Right? Because that is what the rule of probability says. Sum of all probabilities is 1. So basically it's outputting, it makes the neuron output the probability of an item belonging to a class. So when you're dealing with binary classification, when you only have 2 classes, you use a Sigmoid function. When you have multiple classes, we prefer the softmax function. So in summary, we had the Sigmoid function, but the problem in Sigmoid function was that it is not centered around 0 and it has a very low gradient. So we moved on to Tanh function, which had a higher gradient and it was centered around 0. Both of these activation functions have the problem of vanishing gradient, which means when you have lots of hidden layers, the gradient starts to vanish as you move to consequent layers. To solve this, we came up with Relu function, which solves the problem of vanishing gradient, but for negative inputs, it has a 0 output. And to counter this, we finally moved on to Leaky Relu, right? So that was it for this video. I'll be making more videos on programming and seeing the effect of different activation functions. And yeah, thank you for watching.